So now we're going to make pretty close to the same video that we made in the last video. I made some changes, so hopefully it's a little easier to see what's going on here too. So we got the J310 right there on the board. The flat side is facing to the left. The flat side is the front. Left pin is drain, middle pin is source, right pin is gate. So when I swiveled it, so flat side is to the left, we got the gate at the bottom, source in the middle, drain on top. We have it wired up like this, but the circuit's not complete. We're going to put a meter in between the anode, wherever we're going to measure actually, and that positive supply right there. So we have this setup here. The JFET has an IDSS. So that's the current that will pass through when you put a voltage across the drain and the source right there. And you have the gate tied to the source, which is also going to ground right there. It's going to pass a certain amount of current. The J310, you can expect somewhere down to 24 milliamps of current, up to about 60 milliamps of current, according to a data sheet I read a long time ago. And also, this is going to set a current, which is commonly called a current source. Just whatever sets a current is commonly called a current source. But technically, the load, the LEDs in this case, right there, are on the high side, right there. And when you got the load on the higher side of the circuit and your control on the lower side right there, you usually call that, or you could call that a current sink. So generally, when it's setting current on the lower side, it's a sink. When it's setting current on the higher side, it would be a source. But any circuit that sets a current is commonly called a current source, just because the grand scheme of things, it's the source of whatever the current flowing through the circuit. It's controlling it. Now, and then when it comes to the IDSS, that means that the source is directly to ground. So this is not IDSS. I is current, by the way. I haven't been mentioning that. Current from the drain, and then source connected to ground. That's what that double S means right there. If it just says current DS, that would just be current from drain to source when the source is not directly to ground. So we will get back to this. I haven't been explaining that, and we're kind of reviewing stuff, so I'm going to explain a little bit more. Let's get to this. Instead of a 100 ohm resistor, which I did in the last video, now we got 220 ohm resistor. Again, we have that gap right there because current can't flow. We need to pass it through the meter right there. And we are going to measure milliamps of current. I don't have to move the red probe for anything with this meter other than high current. Never have to move the black probe. You can see those things that we can measure right there. Other meters, you may have to move one or both probes, depending on what you are measuring. Just be aware of that. I have one where sometimes you got to move the black probe. And now we will bridge the gap. I'm going to do this again. I'm going to put them backwards. It's okay if you put them backwards. You'll just get a negative voltage. So we have 9 volts at the supply right there. And there you can see, negative 7.75. Just because we got them backwards. And I'm going to go this way right there. So 9 volts at the supply. So a little less than 8 milliamps of current. Once I get the connection, I'm going to bypass one of the LEDs. And it's, you know, going up just a speck, but it's basically still just shy of 8 milliamps of current. So not 100% spot on, but not bad. So that's at 9 volts. Let's just go down to 8. I don't think it'll be quite as close. So I think we might be a little shy for how much current we got to be. 7.66 for the both LEDs. By passing the LEDs, you know, it's went up a little bit. Still, maybe okay right there. It's about 8 milliamps of current. Probably fine. Now, we're going to raise the voltage a lot. Let's just go to 16 volts right there. Double what we just had. So, I know it's going to go up, you know, just a little bit. But still, it's going to be about 8 milliamps of current right there. And it's still just a little shy. So, still not too bad. We doubled the voltage. Current remained the same right there. And is that spot on the same? Not quite spot on, but pretty close. Just going up a speck now at these higher voltages. And that might be getting the transistor a little hotter than what I desire. But in any case, we can adjust the value resistor there as long as we stay below whatever the IDSS is. And I did that in an earlier video, just looking at the power supply. I believe we got 0.033 amps, 33 milliamps of current for the IDSS. And actually, no, this probably did not get too terribly hot. I'm not going to do the mental math very good, but we had about 8 milliamps of current right there. You times that by the voltage on the display right there, and that will be the total power that the circuit has to dissipate. So I did the math on my phone, and it looks like we're actually not doing too bad. So we got 8 milliamps of current, the same as 0.008 amps times 16 volts, and I didn't hit enter yet, but it gives you the number down there, 0.128 watts right there, or 128 milliwatts. The transistor itself has a total device dissipation max, so the total wattage right there, 350 milliwatts, 0.35 watts. So we're still, below half of that. Even if I bypass the LEDs, just the transistor passing the current. Of course, each one of the LEDs is going to drop a couple volts, and so it'll be less power that the transistor has to dissipate when it's not on its own right there. When there's other stuff helping to dissipate the power, in this case by dropping some of the voltage, it will create less heat. And I think the resistor too will also take up some. So we should be fine. But yeah, there you can see. Didn't matter whether it was 16 volts or 8 volts, we got basically 8 milliamps of current flowing through the circuit. Just a tiny variation, but in the grand scheme of things, this is a pretty good current sink right there. But you can also call it a current source. So in the title, I did this in the last video, even though I didn't explain the current sink. I thought maybe some people saw it on the diagram. I realized that after I filmed it. So when I titled it, I put current source sink. And that's why, because I kept saying current source, even though technically it's a current sink, but you can always call anything that sets a current source. So hopefully that cleared up confusion for somebody, because I know that's kind of confusing at first. But, it's pretty simple stuff once you get used to it. So that's it. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.